Okay, we start with a cylinder, and the cylinder's got to have some dimensions. We're going to put the x-axis right through the central axis of the cylinder with the origin at the center point of the cylinder, halfway between the left and right. We're going to let big X be a point on the x-axis, and we're going to try to figure out the gravitational field at point big X due to the cylinder. So, in order to do that, of course, we have to have a density function, a mass density function, and so forth. Cylinder will have radius big R, and ultimately we want to do this for mass density rho of R equals AE to the negative KR, an exponentially decreasing density that depends only on R, so that as we move out from the center, the density decreases. And the density will be uniform along any circle about the origin. That's going to be important. Now, in class we didn't actually get to this, although we see where that would be inserted into the result that we do get. First, we're going to solve this for uniform density rho and finding G of big X at position big X greater than L over 2 along the x-axis, not the big x-axis, it's just plain old x-axis, so along the x-axis. Now, we're going to consider a point x, y, z, and a box with dimensions delta x, delta y, and delta z centered around the x, y, z point. Doesn't necessarily have to be centered because, of course, we're going to do the usual thing. We're going to let that box shrink down to 0 dimensions. And I've just drawn a bigger picture of that box for clearer labeling because, as I said in class, I apparently woke up this morning without the ability to position things coherently on the board. So you're going to have to maybe bear with that. Didn't draw this big enough. So that's a little bigger. And over here, we have the same increment referenced within the cylinder. So we have the point x, y, z, which I didn't label here. I just put a little box around a point. I also drew an R vector from the x, y, z point to the point big X on the x-axis. Now, the R vector is important, obviously, because we define the gravitational field due to a mass big M at a point big X to be G times big M over R squared times the unit vector R over R, where the vector R is the vector from the position of the mass to the point at which we're trying to calculate the field. So there's our R vector, and we discussed this some time ago when we defined Newton's law of universal gravitation. So we're going to want to use the vector notation. Okay. Also woke up without the ability to find simple words. Now the R over R is just a unit vector in the direction from here to here. Okay, so we have our G of X. And also, one thing I didn't do in class that I should have done, if the R vector goes from here to here, this will actually be a negative, so that all our G of X calculations should have a negative in front of them. It's not going to be particularly important for the way we set this up, but it is important for our final result. The reason for that is simply that the gravitational field here is going to be in the direction opposite R. So it's a force of attraction, okay, just in the direction opposite the R vector, as I've defined the R vector here. Okay. Then this is just this written a little bigger. And what I've written up here is your expression for the uniform gravitation, for the Newton's law, universal gravitation. Big G, big M, little m over R squared times the R vector divided by its magnitude. That's the gravitational force. We divide that by the mass little m that we considered to be at the point big X, and we get the acceleration of gravity at that point, just force divided by mass. So we just divide out the mass, whatever mass we might want to put at this point, and we get the gravitational field at that point. And that should be a concept you're familiar with. Okay, so r is a vector from x, y, z to big X, 0, 0. Because, of course, this is on the x-axis. It has 0, y, and z components. This is an arbitrary point, x, y, z, anywhere within the cylinder. So what is the vector r from x, y, z to big X, 0, 0? Well, you should stop and think that through before you look at this. That should be very straightforward. You just, from x to big X is big X minus little x is the displacement, and that's in the I direction. And then the displacement in the y direction is negative y. Displacement in the z direction is negative z. The magnitude of r is just what we get from the Pythagorean theorem, square root of the sum of the squares of the three components. And then our delta G, that'll be our contribution from this, whatever the volume increment is. Okay, the delta G of x is just going to be big G, big M times this vector over the cube of this magnitude. Okay, just by this. Now I've got the cube of the magnitude, r squared times little r. I like to write this with the big R over little r to emphasize the fact that this is a unit vector that's being multiplied by the magnitude of the field. I was going to put a negative in there, but I see I already did. I didn't see it when I looked. I thought I had. Okay. Now, so that's your expression. But of course, now you also have an expression for the mass. What's the mass within this box? Well, it's just the volume of the box, which is delta x, delta y, delta z, multiplied by rho, which is your density. So that the mass is going to be replaced in the next expression by rho delta x, delta y, delta z. And that's going to be the contribution from any, from a box of given dimensions about any point. And we're considering this to be a small box, small enough that the direction of the r vector doesn't change much if you move from one point to another within the box, nor does the distance between these 2 points change by much.